So as you remember, last time we talked about how to solve this. Mic's okay? Is mic working? Okay, good. We talked about how to solve this in the case of constant coefficients. I'm just going to briefly review the general problem we're solving. We're trying to solve this nth order linear ODE. Oops, my constants are numbered the opposite way, but it's just notation. And there's the forcing term. So today we're again going back to the non-homogeneous problem. We really want to figure out how we can find that particular solution. So let me go on here. That's the general problem. This is nth order linear ODE. And as we discussed, the sum of homogeneous solutions is a homogeneous solution. We figured out how to find those in the constant coefficient case. I stated without proof this theorem that if you have continuous coefficient functions and you have the leading coefficient non-zero for all x in some interval of real numbers, and you have this given initial data set y0 to yn minus 1, then there's a unique function phi such that when you plug it into that differential equation, it works. And not just that, it reproduces the initial data set in the proper way. Y0 being the value, y1 being the derivative, and so forth. Again, this being an initial value problem because we're talking about the same value of the independent variable in each piece of data. If they were different independent values, that would be a boundary value problem, which is above our pay grade at the moment. Here's some examples which we do not care about that much. I mean, we care, but we're going on. So the thing I haven't talked to you much about yet, excuse me, is the concept of linear independence of functions. Is that out of frame? Do I need to lower it a little bit? Okay. So we have a set of linear independence of a set of functions is, if you've had linear algebra, of course, it's a subtle thing, because we're talking about linear independence in a function space, right? So really, I can't talk about, I shouldn't talk about linear independence of functions unless I'm also talking about the domain of those functions, some common domain. So for example, here's the subtlety. If I talk about the set x, absolute value of x, this is my go-to example. If I say that this set is S, all right, is S linearly independent or linearly dependent? Well, the answer is yes, unless I'm being a little more careful. I have to also supply an interval of interest, right? So if we're looking at x and absolute value of x for x greater than 0 or equal to it, right? Well, there you have what? You have absolute value of x is equal to x, right? So certainly x is linearly dependent on x, right? On the flip side, if I have the set x, absolute value of x, so this is not linearly independent, this one. But this one will be linearly independent. I have x, absolute value of x for x in the reals, right? So to show you that that's linearly independent, we go back to the usual criteria. We take an arbitrary linear combination, we set it equal to 0, right? And then we try to show that those coefficients are 0. That pragmatically was the most useful calculational tool for deciding linear independence. Bless you. C1x plus C2, absolute value of x equal to 0, right? Now here's the thing. The examples we typically work in linear algebra, we do polynomials, right? So if you want to think about polynomials as functions, the domain is always all real numbers. But here, there's a question as to what the domain should be taken to be. So if I say for all x in the reals, I have this equation not just for one x, but for all x, right? So you can choose different values of x. There's infinitely many equations here as x ranges over the reals. So in particular, if we take x equals to 1, we get c1 plus c2 equal to 0, right? If we take x equals to minus 1, we get c1, minus c1 plus c2 equals to 0. Of course, you can solve this system, and you get 2c2 equals to 0 from adding the equations. You get 2c1 equal to 0 from subtracting the equations, right? So anyway, we get c1 equals c2 equals to 0. As you can see, of course, x and absolute value of x is linearly independent for all, if we take the domain of the functions be all reals. Of course, you can see that we could reproduce this argument provided we take some interval which has at least one positive and one negative number. That alone will suffice. If you took 2-point sets, one positive, one negative, that alone would give you linear independence of these functions, although no one would do such a thing because it's silly. Okay, so I'm just trying to point out to you that linear independence of a set of functions has to be understood with respect to an interval, all right? Which is a point I don't emphasize much in linear because it's kind of a subtle, and it's more about analysis, I think, in some sense than, I don't know what it is. It's just subtle, so it's not that interesting for linear. Okay, so it's useful though, of course, because you don't have to do these kinds of boring algebraic arguments. It's useful if we can find some other criteria to ascertain when a given set of functions is linearly independent, right? So with that, I'm going to put this away and do some writing. Oh, you know, actually I won't. Actually, the writing I'm about to do is not that interesting, so let me not. Not just yet, anyway. So what you would do then, of course, suppose you have y1 through ym linearly independent, right? I want to see what's a necessary condition that comes from that, all right? So suppose that they're linearly dependent for all x in some interval I. So what does that give me? That gives me that the trivial combination has only the zero solution, right? Yes, Landon?
Is the I the last time?
I is the interval.
Actually, it's just an interval.
Yeah, not the integrating factor. No,
Okay.
no, nothing to do with that. So, in fact, the integrating factor is gone. There's, as far as I know, no theory of integrating factors for higher order ODEs.
Okay.
I mean, that's an interesting question, actually. What is the theory of integrating factors for higher order ODEs? I do not know. So suppose this is 0, right? If these functions are linearly independent, what's the only solution in terms of C1 through Cm? Just the 0 solution, right? Okay, great. Now this holds for all x and I. We're assuming I is some interval, which means a connected subset of real numbers. So I can differentiate this. And then I get this linear combination of the derivatives of the functions is equal to 0. And I am also assuming that the functions are at least m times differentiable, maybe at least m minus 1 times differentiable. Usually they end up being smooth, but whatever. Then you differentiate again, right? Now I got this equation involving second derivatives, and I can keep doing this, right, all the way until the m minus 1th one. The reason I just go to m minus 1 is because then I've got 1, 2, ... m equations. I have m linear equations in C1, C2 through Cm. But if we have m linear equations and m unknowns, and we know the only solution is the 0 solution, what does that say about the matrix of coefficients? It's invertible, right? And in terms of a convenient criteria, a calculational tool to capture that invertibility is the determinant. So rewriting that system of equations in matrix form, we have this matrix here of the given functions and their derivatives times this constant vector equals 0. Only the 0 solution is the only solution. That means the coefficient matrix is non-singular, so the determinant has to be not equal to 0. In fact, it has to be, not equal to 0 at all points in the interval of consideration, right? All of this has been said without regard to any specific differential equation. This is just a tool to ascertain linear independence of functions. And in some sense, it's kind of weird, right? Because we're using a determinant on function space. Well, how big is function space? From a dimensional perspective, it's infinite dimensional, right? And yet we're saying something very specific and very concrete about the linear independence of these functions using this finite dimensional tool, this determinant. Now the reason we can do that, of course, is because we're really just looking at this m-dimensional space, which is formed by the span of these vectors. And so this is called the Wronskian. All right, so the Wronskian, what it does is it takes in a certain number of functions and a certain point, x, not x in this case, and it puts the functions in the first row, derivatives in the second row, all the way out to 1 minus the number of functions in the last row, and take the determinant of all that. That's the Wronskian. If it's non-zero on a whole interval, then you can conclude linear independent. All right. Now, there's some subtle stuff. You might say, okay, well, what if the Wronskian's 0 then?
Is it?
What if the Wronskian was identically 0 on the whole interval? Would that then imply linear dependence? You can tell from my tone the answer is no, but you might wonder why. Well, search no further than my silly example over here. What's the derivative of the? Well, I guess it's hard to differentiate the absolute value of x. So to make this more fun, this example, let's put an x in here and make this x squared. I think that's the one. So the Wronskian of this, right? So the function's x squared and then x absolute value of x. Oops. At the point x, let me make it x naught just to be less annoying. All right. So that would be the determinant of what? You got x naught squared, x naught times absolute value of x naught. Derivative of x naught squared, everybody knows that's 2x naught, right? No mystery there. Less people know, but it's actually true that this has derivative 2 times the absolute value of x naught. If you don't believe me, what this is a fun function, y equals x absolute value of x. What that is it's a parabola, upside down, and parabola right side up, glued together. It looks like a cubic, but it's not. It's not as steep as a cubic. It has horizontal slope. Well, I guess cubics have horizontal slope too, but the derivative actually would look like this. I mean, it actually exists. It's just 0 at the origin, so it is differentiable. We have enough derivatives to calculate the Wronskian. Okay, and so you calculate the determinant. What do you get? You get 2x naught squared, absolute value of x naught, minus 2x naught squared, absolute value of x naught, which is equal to 0 for all x naught in the reals. Right? So there you have a Wronskian, which is identically vanishing, and yet clearly you can see from the graph, if nothing else, that the function x times absolute value of x and the function x squared, these are not linearly dependent. They have different shapes. That alone is a criteria, geometrically, for linear independence. Of course, you can see that they're linearly dependent. What? They are linearly dependent for positive reals or for non-negative reals. Non-negative reals or for negative reals, let's say. But not both. But they're linearly dependent for different reasons in the different places. And that's the thing, is you don't have a uniform linear dependence through the whole domain. So that's the quirky thing. You can have an identically vanishing Wronskian because you have different linear dependences in different parts of the domain. But the thing is, when we talk about linear dependence of functions, we only say that the functions are linearly dependent if they're subject to the same linear dependence through the whole domain. And that's the issue. There are many, many differential equations books which have been written which are not clear on this point. And in fact, discussions about this issue go back to the late 19th century. You'll find some of the great mathematicians of the time like quibbling over it. There's papers by Piano, for example, on this. This example is also, it arose in some of those discussions. And this generalizes. If you take x to the n times, I mean, you can generalize this example for third order and fourth order and stuff. All right. Anyway, I don't emphasize that much in the usual course, but I thought it's important to talk about here. Obviously, it doesn't help us solve differential equations too much, so you'll forgive me from taking a break from my tour de force of calculation. Although that's only partially true because we need the Wronskian to understand variation of parameters. So people don't know what determinants are, so I'm introducing it there. Here's some determinants, yay. Now here is an interesting fact. Wronskian Trivia. Suppose you have n minus 1 times differentiable functions on an interval I. Oh, I think I need, that's a typo. What should I have here?
M.
Yeah, m, because I'm talking about m. On interval I. Then if that set of functions is linearly dependent on I, then the Wronskian is identically 0 for all x and I. But the converse is not true, right? You can have, well, excuse me, the converse is this, though. This is not quite a direct converse. I mean, here, conversely, if there exists a point, x naught, such that the Wronskian is non-zero, then it's linearly independent on I. That's true. I mean, you only need one point to be able to solve that system and get that the constants are 0. So one point of the Wronskian being non-zero suffices to solve that C1 plus plus Cm equal to 0. The thing I was talking about over there is a little bit different, right? And so here's that example in my notes. So given that subtlety, right, that the Wronskian being identically 0 doesn't imply linear dependence necessarily, this theorem I'm about to tell you is really kind of surprising. Yes, Landon?
So, like, what about a polynomial, like, because that's infinitely differentiable, would you have to limit, like, take it from 0 to, like,
What about a polynomial? Well, polynomials have, polynomials won't give you weirdness like this. I need some kind of, my intuition is that you only get examples like this when you have like absolute value functions, things that stop being differentiable at some point.
Okay.
But, you know, that's an example. I don't have any idea what the general class of examples for which the intuitive thing fails. But I can tell you this. The Wronskian of a solution set of linear ODEs is really nicely behaved. If you have L of y equal to 0, homogeneous nth order PDE, ODE, duh, on an interval I, all right, and you have n solutions on I, all right, I didn't say that they're linearly independent solutions. I just said I had n of them, possibly repeated, whatever, although they're not repeated. If there exists x naught in I, such that the Wronskian is not 0, then y1 through yn is linearly independent on I. Well, that's actually not surprising. That's generally true for functions. Right? Linear independence is not the tricky thing. Here's the interesting thing. On the other hand, if there is one point, just one point, such that the Wronskian is 0, then that set of solutions is linearly dependent. So the structure of the Wronskian is much friendlier for solutions to a given ODE as opposed to just general sets of functions. So what that means then is there is no nicely behaved ODE which takes x squared and x times absolute value of x as its fundamental solution set. Because if it did, you know, I mean, well, at least not a differential equation which includes both positive and negative numbers as part of its domain of definition, let's say that. All right, so the proof of this requires us to derive something called Abel or Abel's formula. And I'm gonna put this away and do that. You should see that done by hand. So let me do that. So I will derive the second order case for you guys in class. I actually have the nth order derivation in the notes on page, well, this current, I don't know what the page number is currently, but it's in my, well, it's in my chapter 3. You'll find it if you read my notes, but so here it is. Let A0, A1, A2 be continuous on I. That marker's no good. With A0 of x not equal to 0 for all x and I. This one's no good. I will eventually find a working marker. Again, that's what I get for cleaning my office out. Find all my old stale markers I should have thrown out 2 years ago. All right. So then suppose we have a second order ODE. In particular, we have A0 y prime prime plus A1 y prime plus A2 y equals to 0. All right. With solutions y1 and y2 on I. So to say that those are solutions, y1 and y2 on I, what does that mean? What equations do I get if those are solutions? For the record, we get what? A0, yeah, y1 prime prime plus a1 y1 prime plus a2 y1 equal to 0, and same thing with 2's, right? Now we're just going to let these, I'm just going to save these here. I'll call them star. Save those. And now consider the Wronskian. What's the Wronskian? Of y1 and y2. All right, so that would be w, y1, y2 at the point x. So that's the determinant of y1, y2, y1 prime, y2 prime. I'm ignoring the x dependence. I mean, I could erase that and just think of it as a function equation if I wanted to. Here. Aha. All right, anyway, so this is what? This is y1, y2 prime minus y2, y1 prime. That's the Wronskian. All right? Now then what? Well, I can take those red equations and I can solve them. I should have taken star one step further. I can solve these for y1 prime prime and y2 prime prime, right? We need that for the step that follows this. So let's see here. This tells me what? y1 prime prime is what? a1 over a naught, y1 prime minus a2 over a naught. Why can I do that? Right, because a naught, yeah. So because a naught is not equal to 0 for all x in the interval, I get this identity at each point in the interval I of consideration. All right, then what? Then we calculate the derivative of the Wronskian. So what's dw? dw dx, or w prime if you like. So we've got ddx of what is it? y1, y2 prime minus y2, y1 prime. So we got to do product rule, right? So we get like y1 prime, y2 prime, plus y1, y2 prime prime, minus y2 prime, y1 prime, minus y2, y1 prime prime. Now, thankfully, two terms here cancel out, right? See that? These guys, they're gone. And we can take the second derivatives, right? And we can replace those with this stuff up here. What's that do for us? Let's see here. Something really nice happens. So that's y1 times minus a1 over a naught y1 prime minus, oh, it's supposed to be 2, right? Sorry. This is from y2 prime prime, so there's a 2 here. y2 prime minus a2 over a naught y2 minus y2 times minus a1 over a naught y1 prime minus a2 over a naught y1. Again, I think we have some kind of cancellation. I think. What cancels here? You notice we have a product of y1 and y2 with the coefficient minus a2 over a naught from this, and likewise from that. So those terms I underlined in red, well, the product, I mean, those vanish. And we're just left with what? We're left with minus, I'll factor minus a1 over a naught, I'll factor that out. What we got is y1, y2 prime minus y2, y1 prime. Which is exactly just the Wronskian, precisely. That is minus a1 over a naught Wronskian. So, let that sink in here for a second. So we can erase all this, right? We can erase all this and get to the point, which is that in fact dw dx is just minus a1 over a naught w, right? And so we can separate variables. Well, I mean, why am I mean, I don't have to go through this. We proved this last time. What is this? Oh, I guess I should. Sorry, guys. I forget. These don't have to be constants. If they're constants, we solved it last time, right? But these could be functions. So I should be more careful. So this is dw over w equals minus a1 over a naught. Again, a naught is non-zero, dx. Integrate both sides. You get the natural log of the Wronskian. Absolute value of the Wronskian is equal to minus, well, that integral, right? Or we get that the Wronskian of y1, y2 is equal to the exponential. Well, I mean, let's be careful. A constant, right? Some constant times the exponential of minus the integral of a1 over a naught dx. That is known as Abel's formula, which is pretty, I mean, it's pretty nice, right? And if the Wronskian was 0, I couldn't have divided by w, right? But on the other hand, if the Wronskian is identically 0, then you know that 0 is the solution. So like c equal to 0 is allowed by a separate argument other than separation of variables, just like we talked about last time. And but think about this for the theorem, right? If your Wronskian is 0 for one point in the interval for a pair of solutions, that makes this c equal to 0, so it's 0 everywhere.
Implies linear dependence, right?
Yeah, and that. Although I guess you could still worry it doesn't imply linear dependence, given our other discussions. But that at least is true, that if it's 0 one place, it's 0 everywhere. But it's also in fact true that if the Wronskian is 0 everywhere, the functions are linearly dependent, if it's a solution set. It is in fact not true if you take a subset of a solution set. Suppose you have a third order problem, right? And you took 2 of the solutions from that third order solution set. It can be that the Wronskian of those is 0, even though they're solutions. And they could be identically 0, even though those are solutions. I mean, that could be, it's going to be not identically 0. It could be 0 at a point, I should say. That happens. So you got to be really, it's subtle. The strongest theorem, the strongest results I only have for the totality of the solution set. If that is 0 at a point, it's 0 everywhere. If I take a subset of a solution set and I found the like so-called sub-Wronskian, that being 0 at one point does not force it to be 0 at all points. A lot of times you'll have stuff like x times e to the x or something, and at 0 it'll be linear, it'll be 0, but it won't be 0 other places, and that's, well, this confused me once because I was solving a problem with like the third order variation of parameters. You end up calculating sub-Wronskians there. And I got the sub-Wronskian with 0, but then I was like, but these functions are clearly linearly independent. So how am I getting this sub-Wronskian 0? it didn't dawn on me that I was calculating a sub-Wronskian at that point. So there's now in my notes I then go on to show that, and well, let me see here. Where am I? I then go on to show that Abel's formula is also true for the nth order problem. That's the most difficult solution. That's the most difficult problem in my notes. Let me get this back out again. So to prove that, I found it necessary to use the Levi-Civita symbol and really the component formula for the determinant. Come on. Come back to us. You can do it. Sorry, I've almost got this theory stuff out of my system. Just a little bit longer. I'll get back to the calculations. So this would be the Wronskian for n functions. You could take the sum I equals 1 to, I1 to in from 1 to n. This is that completely antisymmetric symbol. The functions, their derivatives, their n-1th derivatives, that completely antisymmetric product of that is the determinant. And then I did stuff like differentiated that. Then you got the n-fold product rule. And then I did some creative index gymnastics and eventually derived these relations and plugged them back into the original thing. After about, an hour or two of thinking about this stuff, you can understand my calculation. There it is, Abel's formula for the nth order problem. So, which is, to me, shocking. I mean, I don't know, to me this is a really weird result, because it's basically saying you only need to look at the coefficient of y and y prime to decide this formula, but there's still a2 and all the way out to an the coefficients, and they're but here a0 is the leading coefficient, so that's significant. I mean, I have the numbering is opposite last time, right? A0 is the coefficient of the nth derivative. This is the n-1th derivative. So anyway, theoretically it's there, is my point. Of course, you can safely not understand that derivation and be very, very good at differential equations, because that's not really differential equations I was doing there. It's something else. So we talk about a fundamental solution set. We talked about that last time. Here's the theorem for existence of the fundamental solution set. If we have a non-homogeneous problem, L of y equals to f, and continuous coefficients for the system on interval I, then there exists a fundamental solution